Welcome student, in this video we will see the synchronous or clocked sequential circuit. The synchronous or clocked sequential circuit are represented by the two models, Murray circuit and Mealy circuit. There are two type of circuits available. So the Murray circuit is nothing but, in this model the output depends only on the present state of the flip-flop. Right, in the Murray circuit there is a present state, next state is there. So the output is depends upon only the present state of the flip-flop, that is called a Murray circuit. In case of Mealy circuit, in this model the output depends on both present state of the flip-flop and the input. Right, the output is depends upon input as well as present state of the flip-flop. Right, so the Murray circuit output depends only on the present state. Mealy circuit, the output depends upon input as well as present state of the flip-flop. So that is represented by the state diagram. What is state diagram? It is a pictorial representation of the relation between present state, input, next state and output. Right? What is the input, what is the output, what is the present state, what is the next state, all are is represented by the pictorial. It's a diagram. Is nothing but the state diagram. Similarly, we have state table also there. How the states are changed is represented by state table. So in this video we will see the details about Mealy circuit. Right? What is the state diagram? What is the state table for the Mealy circuit? Right. Now we'll go to the state diagram. So we already discussed that in this Mealy circuit it is depends upon input as well as present state of the flip-flop. The output is depends upon input as well as present state. So this is nothing but the state diagram for a Mealy circuit. Right? So that there are four states available, A, B, C and D. Right? So because of 4 we have the binary number 0, 0, 0, 1. This is a present state. This is represented the present state. 1, 0, 1, 1. Right? The state diagram, what are the things we have? Input, output, present state, next state. Right? So there are four states available, A, B, C. Because of 4 digit, 4 combination, we have 4 combinations available, 0, 0, 0, 1, 1, 0 and 1, 1. Right? So what is this? This is nothing but this number represented, this is the input, slash another number is there, that is the output. Right? So the first number represented input, second one represented output. Right? Now we will see this one by one. So the A, first we will take the A. Right? So this is the present state, A, B, C, D. Right? The input there are two, we have two combination, it may be x equal to 0 or x equal to 1. Similarly output, when x equal to 0 what is the output, when x equal to 1 what is the output. Right? So this is the Mealy circuit. This is the circuit developed by the Mealy, it is Mealy circuit, Mealy state diagram. There is no change. So present state, so the next state and output. For x equal to 0, x equal to 1, we need to find what is the output when x equal to 0, when x equal to 1. Right? First we will take the state A. Right? So this is input, this is output. When x equal to 0, the output also 0, the state goes to same state only, A goes to A only. Right? So A goes to A when input x equal to 0, for that output also 0. Right? So this is represented by the first diagram. Right? When input x equal to 0, it goes to same state, for that the output equal to 0. Suppose input equal to 1, what happened? The A goes to B, the state changes from A to B. Right? When x equal to 1, see this, when x equal to 1, A goes to B, for that what is the output? It is 0, the output is 0. Right? So when x equal to 0, the output is 0, A goes to A itself. When x equal to 1, the A goes to B, for that output is 0, that is given here. A to A when x equal to 0, A to B when x equal to 1, for that the output is 0. Right? Now we will go to the second state. For that the if x equal to 0, B goes to B itself, for that the output is 1. Right? For B, x equal to 0 means it goes to B alone, for that the output is 1. Suppose the input is 1, x equal to 1, it goes to A to C. Right? B goes to C when x equal to 1. For that the output will be 0, right. So, it is clearly given. So, for B, x equal to 0 mean it goes itself, for that output is 1. B goes to B, output is 1. For B, x equal to 1 mean it goes to B to C. X equal to 1 mean B goes to C, for that output is 0, right. So, it is clearly given. Now, we will go to the third state, C, right. First we will see this. For x equal to 1, x equal to 1 means C goes to C itself, the output is 1, right. For C goes to C alone when x equal to 1, the output also 1, right. When x equal to 0, C goes to D, the output is 0, right. When x equal to 0, C goes to C, the output is 0, right. So, this is a state diagram that is represented in pictorial form, that is given in the tabular form is a state table, right. C is goes to C itself when x equal to 1, the output is 1. C goes to D when x equal to 0, the output is 0. I will go to the fourth state, D. When x equal to 0, D goes to D itself, the output is 0, right. D goes to D itself when x equal to 0, the output also 0. When x equal to 1, it goes to D to A, the output is 1, right. D goes to A when x equal to 1, the output also 1, right. So, we explain all the 4 states, right. So, this A, B, C, D is the 4 states, 0, 0, 0, 1, 1, 0, 1, 1 is the present state. We have to check that what will happen if the input, what is the output. If input is 0, what will happen? If input is 1, what will happen? For example, for A, input is 0 means A goes to A itself, output is 0. Input is 1 means A goes to B, the output is 0. So, that is clearly given here also. A goes to A if x equal to 0. A goes to B if x equal to 1. Correspondingly, the outputs are 0, right. Now, we will see the description. So, what we discussed in the state diagram and state table, that the description is given. State is represented by a circle, also called node or vertex. So, in a circle we represented A, B, C, D. So, that is nothing but state. It is represented by the circle, also called as node or vertex. Transition between state is indicated by the directed lines A to B, B to C, like that, connecting the circles, right. Transition between the state, that is A to B, B to C is given by the directed lines. The line connecting a circle with itself indicates the next state is same as the present state. A to A means that is a line which that is indicate is for that state A goes to A itself, right. The line connecting a circle with itself indicates the next state is same as the present state. The directed lines, we have another thing, directed lines are labeled with 2 binary numbers, right, separated by a symbol, right. So, first one is input, another one is output, right. The directed lines, the A goes to B, in that we have 2 binary numbers separated by the comma, so that the input value is labeled first, then the output value is labeled next, right. So, this is the description about the state diagram represented by the Mealy circuit, right. The states are represented by the circle. Transition between the states are directed by the lines. If the line connecting the circle itself means present state and next state is same. The directed line indicated with the 2 binary number separated by the slash. First number indicate the input, second number indicate the output. So, from the state diagram we can draw we can develop the state table. So, in this video we discuss about the Mealy circuit, state diagram as well as state table. Thank you for listening. Welcome student, in this video we will see the synchronous or clocked sequential circuit. The synchronous or clocked sequential circuits are represented by the 2 models. First one is Murray circuit and Mealy circuit. The Murray circuit is nothing but, in this model the output depends only on the present state of the flip-flop. The output is depends upon only present state. In case of Mealy circuit, in this model the output depends on both the present state of the flip-flop and the input and also the inputs, right. So, the output depends upon inputs as well as present state. So, in both the model we have the state diagram and state table. So, the state diagram is nothing but pictorial representation of the relationship between present state, input, next state and output. So, it will give the pictorial representation between the input, output, present state and the next state. Similarly, we have state table also available, right. So, in this circuit we are going to discuss about the Murray circuit, right. Now, we will go to the state diagram. So, this is the Murray circuit, the state diagram is given. So, there are 4 states available A, B, C, D. A, B, C, D. 4 states are available, is given by the circle. So, inside the number is available. This is nothing but output, only one output. Whatever may be the input, there is only one output. 0 for A 0, B also 0, C 1 and D is 0. So, that is indicated by the state table also. For A 0, B 0, C 1 and D also 0, right. So, this is the present state and output. This output is given by the circle. Inside the circle we have one binary number available, that is nothing but the output. So, this is nothing but input. The input, it has 2 types. X equal to input may be 0 or 1, right. I already know that Murray circuit depends upon only the present state. Present output is depends upon only the present state, not depends upon the input. So, that we are getting the output, the constant output for either x equal to 0 or x equal to 1, not depends upon input, right. So, only it is depends upon the present state, right. Now, we will see the how it is changes, right. First we will take the state A, right. When x equal to 0, this is nothing but input, this is output. When x equal to 0, A goes to A itself, right. For that output is 0. So, x equal to 0 mean A goes to A itself, output is 0. Suppose input is 1, x equal to 1 mean A goes to B, right. So, A goes to B when x equal to 1, for that also the output is 0, right. So, A goes to A when x equal to 0, A goes to B when x equal to 1, in both the case the output is 0, that is given here, right. Input 0 means A goes to A itself, input 1 means A goes to B, right. Now, we will see the next state, we will take the B. Suppose x equal to 0 means B goes to B itself, x equal to 1 means B goes to C, in both the cases the output is 0, right. B goes to B when x equal to 0, B goes to C when x equal to 1, both the case the output is 0, right. So, that is indicated here. Now, we will go to the third state C. When C x equal to 1, it goes to C itself. When x equal to 0, C goes to D, right. C goes to D when x equal to 0. C goes to C itself when x equal to 1, right. C goes to C itself when x equal to 1, C goes to D when x equal to 0, both the case the output is 1, right. So, that is the third stage. We will go to the fourth state D. What will happen? If x equal to 1, D goes to D itself. See this, when x equal to 1, D goes to D itself. When x equal to 0, D goes to A, right. When x equal to 0, D goes to A, right. D goes to A when x equal to 0. So, this is the circuit developed by the Murray, the state diagram, the corresponding state table also available, right. So, there are 4 states available A, B, C, D indicated by the circle. Inside is given as output. The output depends upon only the present state, not depends upon the input. So, whatever may be the input, we are getting the same output 0, whatever may be the input, right. So, that we are getting the only one output. So, this number indicates the input, right. So, A goes to A itself when x equal to 0, A goes to B when x equal to 1, both the case the input is, the output is 0, right. So, this is the state diagram. Now, we will see the description. What is the description given for this state diagram? The director lines are labeled with only one binary number representing the input, right. The directed lines are labeled. From A to B, one line is there, in that one binary number is available that indicates the input. The output is indicated within the circle below the present state, right? There are 4 present state A, B, C, D. Below that one binary number is available. So that is nothing but output. Output is indicated within the circle below the present state, right? The NS is nothing but next state of the flip flop after the application of clock pulse, right? We have present state, the next state, NS mean next state, right? So in this video we discuss about the state diagram and state table of the Murray circuit. Thank you for listening. Welcome student, in this video we will see the state reduction and state assignment. So it avoids the introduction of redundant state. Repeated state can be avoided. Redundant state reduce the number of flip-flop logic gate, reducing the cost of the final circuit, right? So while going with the state diagram, then that reduction of the state diagram and state assignment, we can repeated states can be avoided, so that we can reduce the number of flip-flop, number of logic gates, so that the cost of the final circuit can be reduced, right? Now we'll see the what is the state reduction. When two states are equivalent, one of them can be removed without altering the input and output relationship. That is called a state reduction, right? When the two states are equivalent, we can remove one of the state without altering the input and output, right? Now we'll see the one state diagram. From that we can go for state reduction. So this is the state diagram. The corresponding state table is available, right? This is the present state. This is the next state when input is x equal to 0, next state when x input x equal to 1. This is the output. When x equal to 0, this is the output. When x equal to 1, this is the output, right? So the states are indicated by the circle. So these directed lines, the state from one state to another state. This 0, 0 indicates input and output, right? So we can see this state diagram by relating with the state table. First we will take the A goes to B. If x equal to 0, input is 0, output also 0. A goes to B, input is 0, output also 0. A goes to D, when x equal to 1, output is 1, right? A goes to D, when input is 1, the output also 1, right? Then we will go to B. B goes to F, when x equal to input is 1, output also 1, right? So B goes to F, when input x equal to 1, output also 1. Then B goes to E, when input is 0, output also 0. B goes to E, when input is 0, then output also 0, right? Then we will go to F, we will go in this order, right? F goes to C, when input is 1, output is 0, right? See this, F goes to C, when input is 1, output is 0, right? F goes to C for input 1, but the output is 0. F goes to F itself, for x equal to 0, input is 0 plus output also 0. F goes to F, for input equal to 0 and output also 0. Now we will go to the E. The E goes to F, when input is 1, output also 1, right? This is E. E goes to F, when input is 1, output also 1, right? E goes to E itself, for input and output is 0. E goes to E itself, for input equal to 0, output also 0, right? Now we will go to D. D goes to E, for input and output is 0. D goes to E, for input equal to 0, output also 0, right? D goes to B, for input and output is 1. D goes to B, for input is 1, output also 1, right? Now this is completed. Now we will go to C, right? C goes to D, for input and output is 1. C goes to D, for input equal to 1, output also 1, right? Another thing, C goes to B, for input output is 0, 0. C goes to B. So C goes to B, when input is 0, then output also 0, right? So this is the state diagram, the corresponding state table. We analyze the, from the state table we analyze the state diagram, we analyze the state table. Now we need to analyze what are the repeated terms are available. So in this there are two repeated states available indicated by this blue color, A, B, D, 0, 1. Similarly C, B, D, 0, 1, right? This first and third row are repeated. Similarly, this red color, second and fifth row, B E F 01, E E F 01. So we can avoid these two terms are repeated, we can avoid any one, right? From A B D 01, C B D 01, we can avoid this C B D 01, right? So this C is now represented by the A, right? We are replacing the C with A, so that we can take only A B D 01, right? Similarly, this red color lines, B E F 01, E E F 01, we can avoid this, we can eliminate this fifth line, right? So that this B, this E is now represented by B, right? While eliminating, we need to see how to represent, right? So while eliminating C, this row, the C is replaced by, used by A. Similarly, this E is replaced by, used by B, right? So that now we can eliminate this third row as well as the fifth row. So that is called a state reduction, right? So by analyzing the table, there are two repeated states available, first and third row, second and fifth row. So third row and fifth row is eliminated. The correspondingly C is used as A, E is used as B. Now we'll see the reduced state table, right? Here 1, 2, 3, 4, 5, 6 rows available. Now 2 rows are reduced, only we have 4 rows will be available. We'll go to the reduced state table. So this is the reduced state table. There are only 4 rows available. Second and fifth row is eliminated. So from this reduced table, we can draw the reduced state diagram. See this, now the state diagram is reduced, right? So A goes to B when input is 0, output also 0. A goes to B when input is 0, output also 0, right? A goes to D when input and output is 1. A goes to D when input is 1, output is 1. We will go to B. B goes to B itself when input and output are 0. B goes to B itself when input is 0, output also 0, right? B goes to F in input and output is 1. B goes to F when input is 1, output also 1, right? Now we'll go to D. D goes to B, right, when both input and output is 1, right? D goes to B when input is 0, output is also, both are same. D goes to B only for input and output is 0, for input output also 1, right? For x equal to 0 also output is 0, for x equal to 1 also output is 1, right? 0 0 0 1, right? So D goes to B when input is 0, output is 0. D goes to B also when input is 1 and output also 1, right? Now all the states are covered. This F goes to A, everything. So this is the reduced state diagram, right? So 2 states are repeated, that is eliminated, so that we got 4 row. From that we can draw the reduced state diagram. Now we'll see the description. State assignment. The process of assignment binary value of the state of the sequential machine is known as the state assignment. We need to go for a sequential machine, is nothing but a state assignment. Then rules for state assignment. First one is states having the same next state for a given input condition should have assignment which can be grouped into logically adjacent cell in the K map, right? That is the first condition. Second one, states that are the next state of the single state should have the assignment which can be grouped into logically in the adjacent cell of the K map. So these are all the 2 rules in the state assignment. The separate problem available for state assignment, at that time you are able to know very well. Then transition of the output table. So it can be obtained from the state table by modifying the entries of the state table with the selected state assignment. Then excitation table. It gives information about the excitation to be applied to the flip flop to bring the machine from the present state to next state, right? The entire excitation table we can prepare, so that is applied to the flip flop, that is from present state to next state. So in this video we discuss about the state reduction and state assignment. We discuss one problem, right? We discuss the state table and state diagram. From that we got the reduced state diagram and state table, right? Thank you for listening. Welcome student, in this video we will see the design of sequential circuit. with the solved problem. First we will see the procedure for design of sequential circuit. The first one is obtain the design specification and study the same clearly to understand the operational behavior of the circuit. Second one, construct the state diagram. Third one, develop the state table. Then fourth one is reduced standard form state table by removing the redundant states. Fifth one is state assignment and transition table. Assign the binary values to the states and write the transition table. Choose the type of flip-flop and form the minimal expressions. Then seventh one is draw the K-map and find the minimal expression. Draw the circuit to realize the minimal expression and obtain the above, that is obtain the design of sequential circuit. So, this is a procedure for design of sequential circuit. Now, we will see the problem, solved problem, so that we are able to understand clearly. Now, we will go to the problem. So, the design of sequential circuit, solved problem 1. Design the sequential circuit with D flip-flop. State diagram is given below. So, for designing the sequential circuit, the state diagram is given in the problem itself. Right? State diagram will be available in the problem, available in the question. Here we need to design with the D flip-flop. The sequential circuit has one input and one output. Right? So, it has one input and one output. Now, we will see the state diagram. So, this is the state diagram given in the problem itself, question paper itself, the state diagram will be given. From that we need to frame the state table, right. So, in this state diagram there are 4 states available 0, 0, 1, 0, 1, 1, 0, 1. So, these are all the 4 states, right. So, this is nothing but these lines are nothing but how it is going from one state to another state, right. So, this green color line, the state goes to the same state, the 0, 0 goes to the same 0, 0, that indicate by the green color line. This red color line indicate from one state to another state. These two binary numbers is nothing but first one is input slash by output. The first one input, the second one is the output, right. So, there are 4 states available 0, 0, 1, 0, 1, 1, 0, 1. The states from one state to, it will go from one state to another state or in the same state itself. These two binary number, first one is input, second one is output. Now, from this we can frame the state table. So, this is the present state, this is the next state for 2 cases, for x equal to 0 or x equal to 1. This is the output, for that also 2 case, x equal to 0 or x equal to 1. Now, we will see this. First, we will take the state 0, 0. See, this 0, 0 goes to 0, 0 itself. For input x equal to 0, output also 0, right. 0 is a present state 0, 0, next state also 0, 0. 0, 0 goes to 0, 0 itself. For input x equal to 0, output also 0, right. This 0, 0 indicated here. This is 0, this also 0. Input is 0, output also 0. Then this 0, 0 this goes to 1, 1, right. 0, 0 goes to 1, 1. For input and as well as output is 1 by 1, right. 0, 0 goes to 1, 1. For input x equal to 1, output also 1, right. 0, 0 to 1, 1. This 0, 0 to 1, 1. The input x equal to 1, output also 1, right. So, this condition is over. Now, we will go to this 0, 1. Right, 0, 1 goes to 1, 0 for input 0 as well as output 0. 0, 1 goes to 1, 0 for input equal to 0, output also 0, right. This 0, 1 goes to 0, 0 for input 1, output is 0. 0, 0 goes to 0, 1 goes to 0, 0. 0, 1 goes to 0, 0 for input x equal to 1, output is 0, right. Input 1, output is 0. So, this condition is over. Now, we will go to 1, 0, right. This 1, 0 goes to 0, 0 for input 0, output 1. 1, 1, 0 to 0, 0. 1, 0 to 0, 0. Input is 0, output is 1. The same 1, 0 goes to 1, 1 For input 1, output 0, right. So, this 1 0 goes to 1 1. For input equal to 1, output is 0, right. So, it is clearly from the diagram we can write this state table. So, this is also over. Now, it is 1 1. So, 1 1 goes to 1 1 itself. For input equal to 0, output is 1, right. So, 1 1 goes to 1 1 itself, input equal to 0, output is 1, right. Input 0, output 1. The same 1 1 goes to 0 1, 1 1 goes to 0 1. For input equal to 1, output equal to 0. 1 1 goes to 0 1, for input equal to 1, output is 0, right. Now, from the state diagram, we framed the state table, right. So, what is the present state, what is the next state, what is the input, what is the output, all are available in the state table. From this we need to design the D flip flop, excitation table for D flip flop, right. Before that we will see how many states and how many flip flops are required. The number of state is 4. So, the number of flip flop is calculated from this condition 2 to the power n minus 1 less than or equal to n less than or equal to 2 to the power n. This capital N is nothing but number of states, small n is the number of flip flop, right. First we will substitute n equal to 2. So, 2 to the power 2 minus 1 less than or equal to 4, this is the number of states, less than or equal to 2 to the power 2, that is 2 to the power 1 less than or equal to 4 less than or equal to 4, right. So, this 2 less than or equal to 4 less than or equal to this condition is satisfied. So, we need only 2 flip flop, the number of flip flop is required is 2. We need to substitute n equal to 2, 3, 4 like that. So, when it is the condition is satisfied, the corresponding number we need to take, right. The number of states is 4. From this condition we identified n equal to 2, that is number of flip flop equal to 2. Here we are using the D flip flop. Now, we need to design the excitation table for the D flip flop. I will go to this table. So, this is the excitation table. It is the input x, so output y, that already we available in the table. This is the excitation table. This is the state table what we discussed. I drawn again in order to analyze the this excitation table is designed from the state table. So, that I draw the state table again, right. So, the state table what we discussed earlier, same only. From the state table only we can design the D flip flop. So, that I drawn again, right. So, this is the input x equal to 0, x equal to 1, these are all the outputs. So, the input available, output available. Now, we need to see the present state, these two are present state, this is the next state, current state and next state. For that, what is the input to the DA? DA means first flip flop, DB means second flip flop. We are having 2 flip flop. So, the A is the first flip flop, D is the second flip flop. So, the excitation table aim is we need to find what is the value of D flip flop, what is the value of DA as well as DB, right. This only we need to decide what is the input to the first flop, what is the input to the second flip flop, right. For that we have input, output, current state, next state, right. What is that current state, next state? 0 0 to 0 0, right. So, this 0 0 to 0 0, for that input is 0. What is the output? That also 0, right. 0 0 to 0 0, 0 0 to 0 0, input 0, output also 0. Why I need to identify what is the input to the flip flop A as well as B. How to identify? For that, one more excitation table available for the D flip flop. This is the excitation table for the sequential circuit, right. What is the excitation table? Excitation table means from the current state and next state we can decide the what is the input required to the D flip flop. It is reverse of the truth table. Truth table, from input we can identify the output. Here from the output we are identifying the input. For example, 0 0, current state is 0, next state is 0 mean what is the input of the D flip flop. Current state 0, next state 1 means what is the input of D flip flop, right. In this D flip flop, the current state is not taken into account. What is the value of next state? That is nothing but the input to the D flip flop. Otherwise, the input to the D flip flop will be reflected as a next state. This not bother about the current state. Whatever may be the current state, the next state purely depends upon the value of D input. D flip flop input will be reflected. See this, the D 0 means the next state also 0, whatever may be the current state. D1 means next state is 1. D0 means next state 0. D1 means next state also 1, right? So, the next state and D input both are same. Otherwise, the next state purely depends upon the D input. Otherwise, D input will be reflected as a next state, not bother about the current state. So, based on this, now we need to identify the D value, right? The DA and DB. Okay. Now, see this 0 0 to 0 0, right? So, what we identified from this excitation table, the next state and D input both are equal. Q n plus 1 and D is equal. So, that the next state what is available, that is nothing but the input of the D flip flop, right? So, the next state 0 means D also, DA also 0. 1 means 1, 0 means 0. So, that is what we explained here, right? The Q n plus 1 0 means D 0. Q n plus 1 means D also 1, right? The next state and D input both are same. So, based on that we can write, right? Q A plus 1 is the next state of the first flip flop A. So, that will be reflected as a input of the D flip flop. Both are same 0 0 1 1 0 0 1 1 everything. Similarly, second flip flop, the next state of the second flip flop, that is nothing but the input to the second flip flop. Both are same 0 0 0 0 0 0 1 1 1 1. So, these two values are equal based on this explanation, right? Okay. Now, we will see the remaining terms 0 0 to 0 0, input is 0, output also 0. 0 0 to 0 0, input is 0, output also 0. What is the D input? That is nothing but next state. So, 0 0. 0 0 to, then this will go this 0 1 to 1 0. 0 1 to 1 0, input is 0, output also 0. Input is 0, output also 0. Then 1 0 to 0 0. 1 0 to 0 0, the input is 0, output is 1. Input is 0, output is 1. What is the D value? D value is nothing but next state 0 0 means here also 0 0. Then 1 1 to 1 1, input is 0, output is 1. 1 1 to 1 1, input is 0, output is 1, right? Now, this condition over. Now, go to the next column 0 0 to 1 1, input is 1, output is 1, right? 0 0 to 1 1, input is 1, output also 1. Then 0 1 to 0 0, input is 1, output is 0. 0 1 to 0 0, input is 1, output is 0. 1 0 to 0 0, 1 0 to 1 0 to 1 1, 1 0 to 1 1. What is the input? Input is 1, output is 0. Input is 1, output is 0, right? So, the first 4 case the input is 0, 0 0 to 0 0. For next 4 the output input is 1, right? The output depend upon this value. So, the last one is 1 1 to 0 1, 1 1 to 0 1. What is the input? 1. What is the output? 0, right? So, from this table the excitation table is the for a design of flip flop, the table is created, right? 0 0 to 0 0, 0 0 to 1 1, 0 0 to 1 0, like that, corresponding input and output. The value of D, DA and DB is nothing but the next state of the flip flop. The next state of the flip flop reflected as a D value, right, based on this explanation. The D0 means Qn also 0 irrespective of the current state, right. Now, we developed the excitation design of the D flip flop. Now, we need to identify the expression for DA, DB as well as output Y, right. Using the K map, we need to identify the minimal expression for DA, DB and Y. Now, we will go to the K map. So, the K map reduction, first we will go for the DA, the flip flop, first flip flop, the input for the first flip flop, right? This map is drawn, the input is x, qa, qb. X is the input, qa, qb is the current state. From that only we are going to identify the expression for dA, right? X, qa, qb. X having two options, x bar x, that is 0, 1. qa, qb having 4 options, 2 digit 4 option, 0, 0, 0, 1, 1, 1 or 1, 0. qa bar, qb bar. qa bar qb, qa qb, qa qb bar, right? So based on the table there are 4 ones available. These two ones are grouped together, these two ones are grouped together, left and right corner. While grouping these two ones, what we have here, x bar is there, right? So that x bar is written. Correspondingly, second and third column, qa and qa bar and qa got cancelled, only we have qb, right? So that x bar qb, that is the expression from by grouping these two ones. Then by grouping these two ones, the correspondingly what we have, x is available. We need to verify the first column and fourth column. See this qa bar and qa got cancelled. We have qb bar on both the side. So qb bar, x qb bar, right? So we got the expression for dA equal to x bar qb plus x qb bar, right? Similarly, we can go for the dB. So dB, same thing, x, qa, qb, the three inputs, right? So based on the table, previous table, there are 4 ones available. These two ones are grouped together and these two ones are grouped together. While grouping these two, what we have, same thing, x qb bar. In the previous case also same thing. While grouping these two, what happened? This first row and second row, x bar got cancelled. What is available in the third column? qb qa, right? qb qa. So the dB is nothing but qb qa and x qb bar. That is very similar to the previous case. Then we will go to the y, the output y. The input is x qa qb, right? From the table there are 3 ones available. These two are grouped together, this is available individually alone, right? While grouping these two, correspondingly what we have, x bar. What is available in the third and fourth column? This qb bar got cancelled, only qa is available, right? So x bar qa, right? This one is correspondingly what we have, x here, qa bar qb bar, x qa bar qb bar, right? Now we got the expression for output also. Now we'll go to the implementation of this expression using the logic gates. Now we'll see the design of this logic diagram. There are two flip-flop, D flip-flop. This DA, input is DA and this input DB. QA bar, output, QB bar, right? So now we need to design this QA. The expression for QA is nothing but x QB bar plus x bar QB. That is nothing but XOR gate. X QB XOR gate. XOR gate is, what is XOR gate? A B bar plus A bar B. Similarly, we have x QB bar, then x bar QB. So that is given as a XOR gate, right? So and then DB. DB is nothing but QA into QB. So this is QA into QB. QA and QB is there, plus x into QB bar. This is x into QB bar. These two are multiplied and added together. That is given as a DB, right? DA and DB is given from the previous expression. Now we need to design the y. What is y value? X bar QA, x bar QA. So these two are multiplied. Other one is x QA bar QB bar. These two are multiplied and added together. That is the output. So y equal to x bar QA plus x QA bar QB bar, right? That is the output. So this is the final design of the sequential circuit. So in this video we discuss about the design of sequential circuit using D flip-flop. The state diagram is given. From that state table, design of D flip-flop, then reduction using K map, then the reduced expression is implemented with the logic diagram. Thank you for listening. Welcome student, in this video we will see the design of sequential circuit solved problem 2. Design the sequential circuit using T flip-flop. The state diagram is shown below. The state diagram is given. From that we need to design the sequential circuit using the T flip-flop. The sequential circuit has one input and one output. Now we will see the state diagram. So this is the state diagram given in the problem itself. In the question paper, the state diagram will be given. From that, we need to develop the state table, design of D flip-flop and reduction of the expression, D flip-flop expression. That expression is implemented with the logic gate, logic diagram. Right. First, we will from the state diagram, we will develop the state table. Right. This state diagram, there are 4 states available, 0, 0, 1, 0, 1, 1, 0, 1. So, these are all the 4 states. So, this line indicate the states goes from one state to another state, right. For that, these 2 digits are, first is the input, second is the output. While the state goes from one state to another state indicated by the red color line, for that the input is, first digit is the input, second digit is the output. This green color line indicate the state goes to same state itself. It goes to the current state and second next state also same. So, that is indicated by the green color line. Right. So, there are 4 states and goes from one state to another state or state itself. These 2 digits, first one indicates input, second one indicates the output. Now, we will develop this state table. This is the present state. These 2 are next state for x equal to 0 as well as x equal to 1. This is the output for x equal to 0 as well as x equal to 1. First, we will take the state 0, 0. 0, 0 goes to 0, 0 itself. For input also 0, output also 0. See this, 0, 0 goes to 0, 0 itself, input is 0, output also 0. 0, 0 goes to 1, 1. For input is 1, output also 1. 0, 0 goes to 1, 1, input is 1, output also 1. Right. So, this state diagram we developed the state table. Next, we will take the 0, 1. This 0, 1 goes to 1, 0. 0, 1 goes to 1, 0. For that input is 0, output also 0. 0, 1 goes to 1, 0, input is 0, output also 0. 0, 1 goes to 0, 0. Input is 1, output is 0. 0, 1 goes to 0, 0. Input is 1, output is 0. Right. Next, we will take the 1, 0. See this 1, 0 goes to 0, 0. For input is 0, output is 1. Right. 1, 0 goes to 0, 0. Input is 0, output is 1. This 1, 0 goes to 1, 1. 1, 0 goes to 1, 1. What is the input? Input is 1, output is 0. Input is 1, output is 0. Right. The last one. 1, 1 goes to 1, 1 itself. 1, 1 goes to 1, 1 itself. For input equal to 0, output is 1. Input is 0, output is 1. 1, 1 goes to 0, 1. 1, 1 goes to 0, 1. What is the input? Input is 1, output is 0. Input is 1, output is 0. Right. So, from the state diagram, now we developed the state table. This is the present state, next state for x equal to 0 and x equal to 1. Output for x equal to 0 and x equal to 1. Now, we need to design the D flip-flop. Now, first we need to identify how many flip-flops are required. Right. So, the number of states equal to capital N equal to 4. There are 4 states available. The number of flip-flop is identified from this condition 2 to the power n minus 1, small n minus 1, less than or equal to capital N, less than or equal to 2 to the power n. This n is nothing but number of flip-flop, n equal to 2. If you substitute n equal to 2, 2 to the power 2 minus 1, less than or equal to 4, the number of states, less than or equal to 2 to the power 2. So, 2 to the power 1 less than or equal to 4, less than or equal to 4. So, 2 less than or equal to 4, less than or equal to 4. This condition is satisfied. So, the number of flip-flop n equal to 4, right? This number of flip-flop n is not 4, it is 2. Number of flip-flop equal to 2, right? Now, we need to design the T flip-flop. We decided we are using the T flip-flop. We need 2 flip-flop. For that, we need to find what is the input to this 2 T flip-flop. Now, we will go to the design table. Right. So, this is the 2 flip-flop TA, TB. Right. What we need to identify what is the input to the first flip-flop TA, second flip-flop TB. This is the input. X, this is the output Y, that is available in the excitation table. This is the current state, this is the next state. From current state to next state, we need to identify what is the TA value and TB value, right. First, how to develop this diagram? This 0 0 to 0 0, input is 0, output also 0, right. Now we'll go to the state table that is clearly given. 0 0 to 0 0, the input is 0, output also 0. Similarly, 0 1 to 1 0, input is 0, output also 0. 1 0 to 0 0, 1 1 to 1 1, for that the input is 0, for output is 0 0 1 1. So, this only written in this D flip flop, right. 0 0 to 0 0, 0 1 to 1 0, 1 0 to 1 0 0, 1 1 to 1 1. For all the case, the input is 0, output is 0 0 1 1. Similarly, if the input is 1, these are all the 4 states, for that output is 1 0 0, right. So, this table is developed from the state table, from the previous state table, right. So, input is available, output is also available, present state, next state also available. We need to identify the input for the first flip flop TA and input for the second flip flop TB, right. I think you are able to understand this. 0 0 to 0 0, what is the input, what is the output, right. There are 8 combinations. I will explain the state table again. So, there are 8 tables, that is 0 0 to 0 0, 0 1 to 1 0, 1 0 to 0 0, 1 1 to 1 0, 4 combination. For that x equal to 0. 0 0 to 1 1, 0 1 to 0 0, 1 0 to 1 1, 1 1 to 0 1. For that input equal to 1, output is this one. So, that 8 combination, these 2 and these 2, right. Like that only the design of D flip flop, the tabular column is developed, right. So, now we see this, what is the input for first flip flop TA, second flip flop TB, right. What is the excitation table of T flip flop? From that only we can identify. So, this is the current state, next state, the input to the T flip flop. See this 0 0, there is no change in current state and next state mean the input is 0, the T flip flop input is 0. 1 1, so there is no change, current state also 1, next state also 1, that means there is the T flip flop value is 0. So, both are same, current state and next state both are same means the T value is 0. 0 to 1, the current state is changed from 0 to 1 or 1 to 0 means the T input will be 1, right. So, both the states are equal, the T value is 0. The state changes from either 0 to 1 or 1 to 0 means the T value will be 1, right. So, based on this we can identify the value of the TA and TB, right. First we will see the TA, 0 to 0, no change, so that TA also 0. 0 to 1, change is there, so that 1. 1 to 0, it is the current state and next state is changed, so that 1. 1 to 1, no change, so 0. 0 to 1, changed, so that 1. 0 to 0, no change, 0. 1 to 1, no change, 0. 1 to 0, changed, so that 1, right. Similarly, we can go for QB and QB bar. 0 to 0, no change, so that the input is 0. Then 1 to 0, the state is changed, so that input is 1. 0 to 0, no change, 0. 1 to 1, no change, 0. 0 to 1, changed, so that input is 1. 1 to 0, changed, so that 1. 0 to 1, 1. 1 to 1, no change, current state and next state is same, so that the input is 0, right. Here it is changed from 0 to 1, current state is 0, next state is 1 means the T value will be 1, right. The 0 indicates there is no change in current state and next state, 1 means there is a change in current state and next state either from 0 to 1 or 1 to 0, right. Now, we got the input for TA and TB. Using the K map, we need to identify the minimum expression for TA, TB and Y, output Y. For these 3, we need to identify the minimal expression using K map. Now, we will go to the K map. Now, we will see the K map reduction. We need to identify the expression for TA, TB and Y. For that, the input is X, QA, QB. X is the input, QA, QB is the current state of the flip-flop, right. So, x, QA, QB is taken as the inputs. So, the x having one variable, two combination, x bar x 0 1, QA, QB 2 digits, so that 4 combinations are available, 0 0, 0 1, 1 1, 1 0. 0 0 means QA bar, QB bar. 0 1 means 0 means QA bar, 1 means QB, 1 1 means QA, QB, 1 0 means QA, QB bar. So, from the tabular column there are 4 ones are available. These 4 ones are not able to group, all are available individually. So, that we got the expression x bar QA bar QB plus x bar QA QB bar plus x QA bar QB bar plus x QA QB, right. We got this expression. It is not minimized because not able to grouping. Now, we will go to TB. For TB, the input is x QA QB, right. So, there are 4 ones available. These two are grouped together and these two are grouped together, right and left corner. While grouping these two, this x bar x got cancelled. Only we need to say this second column QA bar QB. So, that is available QA bar QB. While grouping these two, what we have here, x is there. So, x we need to write x. I need to check the first column and fourth column. Here QA bar is available, here QA is available. So, got cancelled. Only QB bar is commonly available. So, x QB bar, right. So, TB value is QA bar QB plus x QB bar. Now, we will go to the y. So, in this y there are 3 ones available. These two are grouped together, this is available individually. While grouping these two, what we have, x bar. Correspondingly, third and fourth column QB bar and QB got cancelled, only QA. So, that x bar QA. While grouping, while analyzing this one, what is have x? Here QA bar QB, x QA bar QB. So, this is the expression for y. Now, we got the expression for TA, TB and y. So, these three expressions should be implemented with the T flip-flop. Now, we will go to the logic diagram. So, we have two T flip-flop available, TA, TB. The corresponding outs is QA, QA bar, QB, QB bar, right. What is the input to the TA? TA is nothing but there are four terms available, 4 are added together. For that we have one OR gate. For multiplying the terms we have 4 AND gates. What is the term? X QA QB. So, corresponding inputs are added together. X bar QA bar QB, X bar QA QB bar. Then last one is x QA bar QB bar, right. These 4 are multiplied together, then added, then it is given to TA. Similarly, TB is nothing but x QB bar plus QA bar QB. These two are multiplied, then added, then given to the TB, right. Now, we have one more term, y is available. What is the expression for y? Y is nothing but is x QA bar QB plus x bar QA. These two are multiplied by the AND gate, then it is added. So, we got the final value y. So, in this video we discuss about the design of sequential circuit using T flip-flop, right. The state diagram is given, from that state table is developed, from that design of T flip-flop is developed, from the design reduced expression for a TA, TB and y is calculated using K-map. That expression is implemented with the T flip-flop in a logic circuit. Thank you for listening. Welcome student, in this video we will see the design of sequential circuit solved problem 3. The problem statement is a sequential circuit with D flip-flop A and B, 2 inputs x and y, output z is specified by the following equation. There are 2 flip-flop AB, input is x and y, output is z, that is specified by the this equation. A of f plus 1, that means next state, equal to x bar y plus x into A. B of f plus 1 equal to x bar b plus x into A. Then output z equal to b, right. So, A, the next state is given as x bar y plus xa, b f of 1 is given as x bar b plus xa, z equal to b. The question is, draw the logic circuit for the given, from the given equation we need to draw the logic circuit. Then derive the state table. We need to obtain the state table. Derive the state diagram. From the state table, we need to frame the state diagram. First, we will go to the logic circuit. Logic circuit very easy. The A of f plus 1 is x bar y plus xa. B is x bar b plus xa. Z is b. So, based on that, we can design the logic circuit. Now, we will go to the logic circuit. So, this logic diagram is available. This is the first flip flop A. This one is second flip flop B. First, we will see the first flip flop. So, this is the x available. With not get, we have x bar also available. This is y available, right? X bar, y is available. This QA is also taken as a one of the, this line indicates QA. Similarly, we have QB also available. This QB also, the output QB also taken, and this line indicates the QB, right? X bar, Y, QA, QB, right? QA, QB is nothing but AB. So, we have 5 inputs are available, 5 data are available here, X bar, Y, QA, QB, right? First, we will see the DA, the expression for A, first flip flop, right? So, this AND gate is available, so that it is nothing but x bar into y. This is x into a, both are added together. So, dA is nothing but x bar y plus xa, that is given to the dA, right. So, that we got the QA. Similarly, dB is nothing but x bar into QB plus x into a. So, these two are multiplied, then added by this OR gate. So, that x bar QB plus x into a is given as dB, right. So, we have all the terms available, x bar available, a, x, everything is available. So, the corresponding lines are connected together, so that we got the required input that is given to the dB also, right. So, the dA and dB input is given. What is the output Z? Output Z is nothing but QB, current state, QB, right. This is QB bar, the QB, the B is nothing but Z. This is given, equation is given, Z equal to B. So, that from B we got the output, right. Now, we drawn the logic circuit. Now, we will go to the state table. So, this is the state table available, right. This is a present state, next state and output. For 4 combination, 4 states are there, 0, 0, that is x equal to 0, y equal to 0. There are 2 inputs, x equal to 0, y equal to 0, the output. Similarly, 0, 1, when x equal to 0, y equal to 1, then 1, 0, x equal to 1 and y equal to 0, then 1, 1, right. So, the state table is obtained for 4 combinations, 0, 0, 0, 1, 1, 0, 1, 1, because there are 2 inputs available, x into y. So, the 2 inputs mean where we have 4 combinations are available, 0, 0, 0, 1, 1, 0, 1, 1, right. The present state, again the QA, QB, so the 4 combinations, 0, 0, 0, 1, 1, 0, 1, 1, right. From this, we need to identify the next state. How to identify the next state? The equation is given, A of f plus 1 equal to x bar y plus xa. Similarly, B of f plus 1 equal to x bar b plus xa. So, by using this equation, we need to identify what is the next state. Now, we will see that QA equal to 0, QB also 0, x also 0, y also 0. Then we will see that what is the output. Z is nothing but B, right. Z equal to B, right. So, that the Z can be easily obtained from the value of B, right. This 0, 1, 0, 1, 0, 1, 0, 1. Similarly, this 0, 1, 0, 1, right. Current state is nothing but the Z value. Output is easily calculated, Z equal to B. So, the B value is nothing but output value. Now, we will see the next state, QA plus 1, by using this equation. Here all are 0, x is 0, y 0, a 0 and b also 0. So, x bar into y, y is 0, x is 0 mean x bar will be 1. So, 1 into 0, again 0 only. X is already 0, a also 0. So, 0 plus 0 we have 0, right. The QA plus 1 is 0. Similarly, B value. This x bar, x is 0 means x bar will be 1, b is 0. So 0 plus 0 into 1, 0 only. X is 0, a also 0. So totally we have 0. Right. Now we'll go to the next combination. A is 0, b is 1, and x and y is 0. Only b is 1. Now we'll substitute that. So x bar means 1 into 0, that's 0 only. This also 0 into 0, 0 only. Now we'll have this x bar, x is 0, x bar is 1. What is the b value? B value is 1. So 1 into 1, we have 1 is there. But this is 0 into 0, becomes 0. So 1 plus 0, 1. Right. So by substituting these values, a value, b value, x and y value in this equation, we can easily identify the next state. Right. Similarly, we will find this. A is 1, other terms are 0. So x bar is 1, this is 0. So totally it become 0. Only a is 1, but x is 0. So totally 0. Right. So similarly, we can identify the value of other terms. For example, 0, 1, 1, 0 as well as 1. Right. So we have 4, here 4, here 4, and another 4, 4. 16. The 16 combinations are available. Right. For 0, 0, 4 combination, 0, 1, 4 combination, 1, 0, 4 combination, 1, 1, 4 combination. So by using this, we need to draw the state diagram. What is state diagram? 0, 0 goes to 0, 0, the output is 0. That is 0, 0 goes to 0, 0 itself, for the output is 0. Similarly, 0, 0 goes to 1, 0, for that output is 0. Similarly, 0, 0 goes to 0, 0 itself, output is 0. 0, 0 goes to 0, 0 itself, for output is 0. Right. So the 0, 0 goes to 0, 0 itself for 3 cases. Only in one case, 0, 0 goes to 1, 0 with the output of 0. Now we will verify that state diagram. We'll check the, we'll develop the diagram. See this, 0, 0 goes to 0, 0 itself for 3 cases, 0, 0, 1, 0 as well as 1, 1. For all the case, output is 0. Then what about 0, 1? The 0, 0 goes to 1, 0, 0, 0 goes to 1, 0. For a corresponding, the input is 0, 1, the output is 0. Right. So from the table, it is clear that 0, 0 goes to 0, 0 itself for these 3 combination. Only one combination, 0, 1, it goes to 1, 0. So similarly, we can go for other terms, that is 1, 0, sorry, 0, 1 goes to 0, 1 itself, for 0, 0 output is 1. This 0, 1 goes to 1, 1 for 0, 1 with output 1. Right. This is over. This 0, 1 goes to 0, 0 for 1, 0, 1. So like that we can develop the state diagram. We will go for one more combination. So we will take these two and these two. 1, 1 goes to 1, 1 itself for output 1. Here also 1, 1 goes to 1, 1 itself for output 1. Right. So that is clearly given here. 1, 1 goes to 1, 1 itself for the value of 1, 0 as well as 1, 1. Similarly, 0, 1 also. In only one case, 1, 0, that is another case 0, 0. Right. This 1, 1 goes to 0, 1 for only case 0, 0. Right. So from the state table, we can draw this state diagram. There are 16 states available. Right. So we can develop the state diagram. So in this problem, we discuss about the design of sequential circuit. The equation is given. From the equation, logic diagram is drawn. Then state table is developed. For 2 input, there are 4 combinations, 0, 0, 0, 1, 1, 0, 1, 1. 2 inputs x, y, having the 4 combination, x equal to 0, y equal to 0, like that, 0, 0, 0, 1, 1, 0, 1, 1. From the state table, state diagram also developed. Thank you for listening. Welcome student, in this video we will see the design of sequential circuit solved problem 4. The given problem is realize the sequential circuit for the state diagram using the D flip-flop. The state diagram is given. For that we need to design the sequential circuit using the D flip-flop. So there are 3 states available, A, B, C, that is 0, 0, 0, 1, 1, 0. This number indicates is the output. This x is nothing but the input. For input x equal to 0, x equal to 1, right. So, the 3 states available, that is A, B, C, that 0, 0, 0, 1, 1, 0. The number available inside the circle is the output. This green color number is nothing but a input. So, from this we need to develop the state table, right. From the state diagram, first we need to develop the state table, right. So, see this, the A goes to B for x equal to 0 as well as s equal to 1, right. So, this is the present state. This is the next state for x equal to 0, x equal to 1. So, A goes to B for x equal to 0, A goes to B for x equal to 1 also, right. See this, A state A is go to the state B for both x equal to 0 and x equal to 1, right. For both x equal to 0, x equal to 1, A goes to B. The output is 0. Then the next one, B goes to C for x equal to 0 as well as x equal to 1. B goes to C for x equal to 1 as well as x equal to 0 as well as x equal to 1. The output is 0. Then C goes to C itself for x equal to 0. C goes to C itself for x equal to 0. C goes to A for x equal to 1. C goes to A for x equal to 1. What is the output? Output is 1, right. So, the output here 0, 0, 1, 0, 0, 1, right. So, from the state diagram we developed the state table. So, there are 3 states available. So, we need a 2 flip flop. We are going to use the D flip flop. Now, we need to go with the state assignment, right. How the state, that present state and next state of the D flip flop, right. So, there are 3 states available. Now, we will see this state assignment. There are 3 states 0, 0, 0, 1, 1, 0. 1, 1 is not available, only 3 states 0, 0, 0, 1, 1, 0, right. So, how it is changes? This A goes to B for x equal to 0 as well as x equal to 1. That is, what is B? B is nothing but 0, 1. A is 0, 0, B is 0, 1. So, A goes to B for x equal to 0 as well as x equal to 1, right. So, 0, 0 goes to 0, 1 for x equal to 0, 0, 1 for x equal to 1 also. The output is 0, right. So, the A indicates 0, 0, B indicates 0, 1, C indicates 1, 0. So, here A goes to 0, 0 goes to 0, 1, similarly 0, 1 for both x equal to 0, x equal to 1, that is given here. 0, 0 goes to 0, 1 for x equal to 0, again 0, 1 for x equal to 1 for a output of 0. Similarly, B goes to C for both x equal to 0 as well as 1. So, B is 0, 1. What is C? 1, 0. So, 0, 1 goes to 1, 0 for x equal to 0 as well as x equal to 1, the output is 0. Then C goes to C, that is 1, 0 goes to 1, 0 itself, right, for x equal to 0. Similarly, 1, 0 goes to 1, 1, 0, 0, 1, 0, C goes to A. So, 1, 0 goes to 0, 0, for that output is 1, output is 1, right. Now, we got the present state and next state of the D flip flop, right. I think you are able to understand. A goes to B for x equal to 0, x equal to 1. B goes to C for x equal to 0 as well as x equal to 1. C goes to C itself for x equal to 0. C goes to A for x equal to 1. The corresponding outputs are 0, 0, 1. Now, we need to identify the excitation table, that is the design of the D flip flop. From this from the present state and next state, we need to identify what is the input to the first flip flop and second flip flop, DA and DB. I will go to the next table. First, we will see the excitation table for D flip flop. What is the excitation table? For a current state and next state. For a current state and next state, what is the input to the D flip flop is nothing but excitation table. Truth table means input, output is obtained from input. Here, this input is obtained from the output. From current state and next state, what is the input to the D flip flop? For example, 0, 0, 0, 1, 1, 0, 1, 1. The nature of D flip flop is, it is not bother about the current state. what is the next state that will be reflected as a input of the D flip flop. For example, q n plus 1 0 means D also 0. Otherwise, if D equal to 0, the next state is 0 only. It will not bother about current state. If D equal to 1, the next state also 1. Not depends upon current state. If D equal to 0, the next state is 0. D equal to 1, Qn plus 1 is 1, right. So, Qn plus 1 is very similar to D input. Otherwise, the D input will be reflected as a next state, that without considering the current state, without bothering the current state, right. These two are same. D value will reflected as a Qn plus 1. So, based on that, we can develop the design table for D flip flop, right. So, this is the input X. This is the, we need to decide this DA and DB value, right. From this table, we need to develop this. That is 0 0 goes to 0 1, 0 0 goes to 0 1. This 0 0 goes to 0 1 for a input of 0. Similarly, 0 1 goes to 1 0, 1 0 goes to 1 0, right. So, for all the cases, the input is 0, the input is 0, x equal to 0, right. 0 0 to 0 1, 0 0 to 0 1 for x equal to 0. 0 1 to 1 0, 0 1 to 1 0 for x equal to 0, right. So, this here x is available, this x is available. Similarly, 1 0 to 1 0, 1 0 to 1 0, the corresponding input is 0. Then 1 1 is not available, so it is not considered x mark. For that, input is taken as x. Then similarly, the next one, 0 0 goes to 0 1, the corresponding input is 1. 0 1 goes to 1 0, corresponding input is 1. Similarly, 1 0 goes to 0 0, corresponding input is 1. That is given in this, the remaining table. 0 0 goes to 0 1, 0 1 goes to 1 0, 1 0 goes to 0 0, this is 1 0 goes to 0 0, the corresponding x value is 1. For 1 1 is not available, so that is considered as don't care condition, right. So, from the above table, this the combination of 8 combinations are developed, current state and next state, the input is available, right. I think you are able to understand, right. 0 0 to 0 1 one state, 0 0 to 0 1 another state, for x equal to 0, x equal to 1, right. So, that we are getting the 8 combination, out of which 2 combination is not applicable, right. Now, we need to decide the DA value. We already discussed DA value is purely depends upon next state. So, QA is available, QA plus 1 is available. So, the DA is purely depends upon QA plus 1 next state, it is not depends upon the current state. What is the value of QA plus 1? That will be reflected in the DA, right. See this 0 0 1 1 1 1 XX, same thing. What is available QA1? That is nothing but the DA value. Similarly, QB1 is the DB value, right. So, based on the nature of the D flip flop, it is depends upon the next state, not depends upon the current state. So, based on that, these values are decided. Now, from this value, we need to draw the K map. We need to go for the reduction of the K map. We need to identify the reduced logical expression for DA as well as DB. From the reduced logical expression, we need to design the logic circuit using the D flip flop, DA and DB. Now, we will go to the K map for the reduction of expression. So, first for DA, what is the input? X, QA, QB. X is the input, QA, QB is the current state. So, the DA depends upon the input X, QA and QB, right. So, this X having one variable, so 2 combination X bar and X, that is 0 1, QA, QB 2 variable, 4 combinations are available, 0 0, 0 1, 1 1, 1 0, QA bar, QB bar, QA bar, QB, QA, QB, QA into QB bar, 0 means there is a complement. So, based on the table, there are 3 ones are there and 2 cross mark, 2 don't care conditions are available. So, that these 4 cells are combined together. Similarly, these 2 cells are combined together. So, while combining these 4 cells, the corresponding row we have X bar and X. So, that got cancelled. The corresponding second column and third column, what we have, QA bar and QA got cancelled, only we have QB, right? QB only available. So while combining these two cells, corresponding row is we have X bar. What is available in corresponding column? QA, QB, QA, QB bar. So QB, QB bar cancel, only we have QA. So X bar into QA. So the DA equal to QB plus X bar QA. Similarly, we can go for DB. So the DB same, input X, QA, QB. X bar X and 4 combinations. There is 2 ones are available and 2 don't care conditions are available. So only these two are grouped together. So while grouping, the corresponding row got cancelled, X bar X cancel. Only we have corresponding column, QA bar, QB bar. So the DB equal to QA bar and QB bar. Now we got the expression for DA, QB plus X bar QA, DB, QA bar, QB bar. So based on the equation, we can develop the logic circuit, right? See this, here X is available with NOT gate is connected, so that we got X bar, right? So this is the DA and DB, first flip flop and second flip flop. What is DA? DA value is nothing but QB plus X bar QA. See this here, this is OR gate, so it will add, QB will be added plus this AND gate, so it will multiply both X bar into QA, that will be added with QB. So X bar QA plus QB will be given as a DA value. Similarly, what is DB? QA bar QB bar, right? So this, see this QB bar, this QB bar is taken as one of the input and QA bar is taken as one of the input. So both are multiplied and given as a DB, right? So DB is nothing but QA bar, QB bar. QA bar available here, QB bar available here. Now we design the logic circuit. So in this problem, the state diagram is given, from that state table, then excitation table, then the state assignment and the design of T flip flop, the current state and next state, input to the DA DB is designed. From the tabular column, the reduced expression is got from the K map. The reduced expression is implemented in the logic circuit. Thank you for listening.